All right, let's look at solving problems of two-dimensional elastic collisions and two-dimensional inelastic collisions. This little walkthrough, you can do it on your own. So if you feel like you want to try it on your own, just hit pause and then you can follow along afterwards, see how you do, and see if it makes sense. All right, so having read over it, you'll see that there's a glancing collision between two objects here. And this mass is moving, hits this mass, one goes down, one goes up. One's at an angle of 30, the other one we don't know the angle, and we don't know the speed. Now, in this activity, they're using primes. You could easily use V2I, V1I, V1F, V2F, and in fact, I'm going to adjust that here. And you can make that same adjustment because later on I did change it to V1I and V2I and V1F and V2F. Now, here's the thing. We're trying to figure out what the velocity is of this second one. We already know that this one is moving off at 3 meters per second at an angle of 30 degrees, and this one we don't know. Both the angle and the speed, which is therefore the final velocity. Is kinetic energy conserved? We're going to find out. Just because it says it's an elastic problem, we don't know if it's completely elastic, so we don't know if energy or kinetic energy is completely conserved. However, we always know that momentum, no matter what, is conserved in a collision. Momentum is always conserved, and as long as you neglect these external forces. Momentum is also a vector, meaning that this is the key part, and we could do an investigation to show this as well. This means that the momentum must be conserved in both the x direction and the y direction. So what we can do is break this thing up into components. So look at the x direction. That's positive x direction, and the y direction. So positive x and positive y direction. If we can break the momentum up into x and y components, we can say, well, we already know that in every case before for linear momentum that momentum is conserved. So therefore, in the x and the y directions, momentum should be conserved. Okay. Now, it says here, what is the total x component of momentum before the collision? And what is the total y component before the collision? Now, we're going to look at the two objects. So we know that it's going to be P1x plus P2x initial and P1y initial plus P2y initial. Now, this first block is stationary. So we know that the x momentum and the y momentum for each is 0. We know that. And then we just look at the P1 P1xi. So if we write this out, it's M1 V1I plus M2 V2xi. I forgot the x. And this is M1 V1yi plus M2 V2xi. This 0, this 0. So we have simply in the x direction, it's M1 V1 xi, and down here it's M1 V1 yi. And we look at that and we say, oh, okay, wait a second. In the x direction, this object at the beginning here is simply moving to the right at 5 meters per second with 1 kilogram of mass. That is the x component. There is no y component. And there we go. So the total x momentum before the collision is simply 5 kilogram meters per second. It's 1 times 5. This has 0, and it's all in the x direction. There is no y momentum. Okay. How does this help us? Well, Since there is only an x momentum before they collide of 5 kilogram meters per second in the x and 0 in the y, the momentum must be conserved in both of those directions. So that means, what is the total x and total y components of the momentum after the collision? And I wrote here, think about conservation of momentum. Well, clearly the final total x momentum is going to be the P1xf plus P2xf, P1yf plus P2yf, okay? And we don't even care what P1xf is and P2xf is, what the final momentums are of those two objects, because we know that since momentum's conserved, it better equal 5 kilogram meters per second. And in the y, the final momentum total, both the first object's final momentum and the second object's final momentum, had better be 0, because momentum is conserved in both x and y directions. So we just look and we say, well, the total x momentum was 5, so the final x momentum has to be 5. The initial y momentum was 0, so the total final y momentum must be 0. Okay, let's see how this helps us out. It says, what are the x and y components? So the next part says, what are the x and y components of momentum of mass 1 after the collision? So here I wrote P1xf. Okay, so P1xf is here is going to be, now if you look at your diagram, the x momentum. So this, if we think about the momentum here, it's P1xf. There's a component here called P1f is that total, and then this is P1xf, and there's a vertical component of P1yf, like that. And this is P1f. Okay, so P1f is the total momentum. Well, the total momentum, we know that mass 1 is 1 kilogram, and that's 3. So this is going to be 3 Newton meters, or 3 Newton seconds, or 3 kilogram meters per second. And it's broken into an x and a y component. So how do we write it? Well, we write it as P1f, and it's the x, so it's going to be cosine of the angle, and P1f, sine of the angle. All you need to do is you grab your calculator and you look and you say, okay, well, that's simply P1f was 1 times 3 cosine of 30 degrees, 1 times 3 sine of 30 degrees. So we just look and we say, okay, well, what's cosine of, so 30 cosine times 3 is 2.598 kilogram meters per second. 30 sine is a half. This is 1.5 kilogram meters per second. Okay. So you think now, okay, well, this means that this first object is carrying 2.598 kilogram meters per second of momentum upwards. And sorry, to the right, and 1.5 kilogram meters per second upwards. So now you realize, okay, if I'm trying to figure out the other one, we know that the total x momentum is P1xf plus P2xf, and the final y momentum is P1yf plus P2yf. So if you were trying to find P2xf, it's going to be the total x momentum minus P1xf. The final y momentum minus P1yf. Okay. Well, what was PXF? PXF was 5 kilogram meters per second. minus P1XF was 2.598, like this. And so we know that it was 5 minus 2.598. So 2.4 kilogram meters per second is how much the second object is carrying in the x direction. So you look and you say, oh, okay, well, the first object was carrying 2.598 in the x. This is carrying 2.4 in the x. 2.4 plus 2.598, which is basically 2.6, is 5 to the right. And that's what the total momentum was to the right. So that makes sense. You can answer this next one super easy. The total momentum in the y direction was 0. So therefore, the final momentum in the y direction was 0. So if this object, the first one, was carrying 1.5 kilogram meters per second up, this one must be carrying 1.5 kilogram meters per second down, so that they balance out completely and come out to 0. So here, oh yeah, the total y momentum was 0 minus P1YF, which is 1.5. And there you go. 1.5 minus 1.5 is 0. And we know that the total momentum before the collision in the y direction was 0. The total momentum in the x direction, or in the y direction after the collision, is also 0. And so therefore, when you see the 1.5 subtract the 1.5 giving 0, it makes sense. So then it says from P2XF and P2YF, find V2XF and V2YF. So now we're just finding the velocity. So the V2XF was 2.4 divided by the mass, and the mass of the second one for the first time was 2 kilograms. So you just put in 2.4. Well, this is easy to do in your head. 1.2 kilogram, 1.2 meters per second. And in the y, it's P2YF, which is negative 1.5 divided by 2. And again, you don't need a calculator for this. It's simply negative 0.75 meters per second. So the final velocity, it was 1.2 meters per second this way. It was 0.75 meters per second this way. And so there's your final velocity. So your V2F is square root just use Pythagorean theorem. So you do 0.75 squared plus 1.2 squared. Square root is 1.41 meters per second. And the angle that it makes is 0.75 divided by 1.2, opposite over adjacent. And so that's the inverse tan, 32 degrees. So therefore, the final velocity of that second particle is 1.41 meters per second, 32 degrees down. So now we just solved the problem in two-dimensional space for this problem. And that's all you need to do. That's how you solve problems. You just write out the components and get them to match. So whatever the total x components were, make sure the final x components of the two particles equals that for the momentum only, not the velocities. And then whatever the total y momentum was, make them balance with the final y momentum. That's all you have to do for those types of problems. Okay, in the next tutorial, we're going to look at how to calculate it for inelastic collisions. And then in our third tutorial, we'll try some examples.